Hello, everyone, and I would like to thank the organizers from Early New Year's from Home for inviting me to talk here. Today, I'm Gordon Lee from National Taiwan University, and today I'm going to talk about propagator positivity for cosmological correlators. Now, the big picture here is that we would like to expand the scope of the cosmological bootstrap. So you may have heard of this idea where we want to fix and constrain cosmological correlators just from physical principles alone. For example, using symmetry, it gives us differential equations for understanding like massive exchange processes. Unitarity gives us cutting rules, which gives us the consistency relation, for example, between like 4-point and 3-point functions. And locality gives us something called manifest locality test for master scalars. Now, these are all very powerful tools. However, a lot of these technology is focused on fixing the possible kinematics. And if you contrast that with the other bootstrap methods currently out in the market here, you find that they are doing so much more, right? For example, in conformal bootstrap, you are not just fixing like the possible form of the 3-point function in terms of kinematics. If you use, for example, unitarity, crossing, etc., you can also make statements about what the possible spectrum OPE coefficients can be. Or in the case of amplitude bootstrap, you can also use this physical principle to give constraints on, for example, Wilson coefficients in EFT. And this is the kind of thing we would like to develop, right? We would like to understand how physical principles can constrain parameters in the inflationary models, which will help us verify or which will help us understand and verify different inflationary models. And the best way to proceed about create to understand how to bootstrap these parameters is to exploit positivity. Now, I'm going to reveal the simplest version of this story in amplitudes. So consider an amplitude which only depends on menu sum s. So it's kind of coming for example, from some kind of single channel process, right? Now, this type of amplitude admits a spectral representation, which is this form here. Now, rho here is what we call the spectral density. And it's quite easy to see that once you take the imaginary part of the amplitude, you just get rho here. However, you can use unitarity to show that this has to be larger than zero. The imaginary part of amplitude has to be larger than zero. So by extension, you find that rho has to be positive. Now, and how do you exploit this fact, right? Now, first let's do the following, right? Let's write the amplitude in the power series in the Mendelssohn S. So we have these as Cn here. Now we can actually match this to the tree level amplitude computed by the following EFT. So just a phi squared box and phi squared, and it's easy to see why this works, right? Because every time you have box, it just gives you S. So the tree level contact diagram of this guy will give you this amplitude. Now, likewise, given the amplitude, you can easily figure out what the Cn should be. You just use elementary complex analysis, right? You divide this by s to the power n plus 1, do some contour integral. Now, you can actually then relate this to rho in the following way, right? Suppose you know that A falls off sufficiently fast as s goes to infinity, right? You can blow up the contour, and because there's a branch cut in the real axis of the compass S plane, you just pick up the contribution around that branch cut, which gives you that discontinuity, which effectively gives you imaginary part. And so this is why you can just write Cn in terms of an integral over rho. Uh, so now we're usually interested in we're interested in understanding EFT, and those comes with a cutoff lambda, right? So we define this quantity Gn here. So it's almost the same as Cn. However, the main difference here, aside from some rescaling, is that the lower limit here is changed from 4m squared to this cutoff squared. In practice, what this means is that you can obtain Gn by Cn, but subtracting by things that you can describe inside your EFT, for example, like some mass poles and so on. And now we would like to understand the possible constraints on Gn. Now, the first thing is that Gn is positive because rho is positive and everything else in the integrand is also positive. However, there are more things you can actually say. So, for example, like Notice that in this range of integration, right, S prime is strictly larger than lambda squared, right? So as you increase n, the integrand for gn plus 1 is actually strictly smaller than gn, which tells you which eventually tells you that gn has to be larger than gn plus 1. Now, this type of integral also obeys for some kind of Cauchy-Schwarz equation, which is given by this equation here. And the idea is to take all of these equations and then impose them on the in the parameter space to see what kind of constraints it gives. So here's an example, right? Suppose we truncate at the n equals to 4, fix G2 to be some value, and then we try and see what the allowed space of G3 and G4 is. It's quite easy to see that it actually just becomes an equation like it actually becomes a region like this, right? So it's a very restrictive region here. Everything outside is forbidden by positivity. But this kind of story, you can repeat it for just even if you truncate a high end, you can also repeat this, right? Just take these constraint, and then generally this constraint in your higher dimension parameter space will carve out some kind of a convex region. And this is exactly the kind of story we would like to export to cosmology. Now, how do we export the story to cosmology? Well, the key here is to utilize the split representation of the propagator, or maybe I should say the correlator. So, for example, the time-ordered correlator would be plus plus here, and then the anti-time order would be plus minus, and the Whiteman would be like no, the Whiteman would be a plus minus, and then the anti-time order would be the minus minus. So here F are the mode functions. And now let me emphasize a few things about this expression. So the first thing is that this new here, this integral variable here, new is essentially the Casimir of the zeta isometry group. So it plays essentially the same role as as a S in the flat space story. Eventually, we would like to expand this sigma AB in terms of a series of new. Now, the second thing is that even though I've used the word even though I've been using the word propagator, this has a larger scope of applications. So generally, you can obtain, for example, correlators for conformally coupled scalars by doing this kind of integral. Then you can further, for example, use some differential operator to convert these kind of things to a correlates with master scalars with master scalars. And essentially, the idea we're exploiting is that if you have a single channel process, it doesn't really matter how many external legs you attach to each of these vertex, right? For example, in flat space, the amplitude will only define the exchange Mendelssohn S, and this is the property that we would like to exploit here. Now, the first thing I would like to emphasize is that some people would refer to this as the spectral representation. However, in practice, this sigma AB actually plays more of a role of the amplitude rather than plays more of a role the amplitude rather than the spectral density. So, for example, for the three-level exchange, right, sigma plus plus is actually given by this. So notice how it looks almost like a S minus M square, right? Because mu is actually just related to the mass. However, you also have this. However, now you have to add both terms. You have to have two terms with different I epsilon prescription. And what happens is this additional term here is actually encoding particle production in the zeta. And this guy is actually exponentially suppressed by the mass of the particle. Now, in any case, these generally these kind of these sigma AB are related to each other. For example, you can flip plus and minus by taking complex conjugate these things, or add them together to sum to zero, etc., etc. But we would like to pick a particular combination so we can play this positivity game, and this is the combination that we choose. And it's easy to see why, for example, in the case of three-level exchange, what it does is that it picks out the term with one of the I epsilon prescription, for example, this one here. Once we do this, well, we then just take this because this is kind of the amplitude, right? We write down a spectral representation for this guy here, the sigma nu, and then we just repeat the argument in flat space. So by unitarity, we see that rho has to be positive. So So essentially, the end game is to define some kind of just to repeat the argument and then define some kind of quantity like Gn, which just like in flat space, and understand the constraints here. However, an important caveat is to understand what kind of EFT you should be using. Now, it turns out that generally you should be using some kind of init EFT, which is of the following form. Now, notice that there are this term here, which are like this imaginary terms here. The reason why you need is necessary to include this kind of terms here is that because of particle production in de Sitter, right? Suppose you want to integrate out some heavy field, right? But because of particle production, you still need to account for those. And the way you account for them is to introduce this imaginary part. However, in practice, these terms are generally suppressed by the mass of the heavy particles, so they're usually very small. Now, once you have this series, now you find that okay, after you take account of these exponential factors, right? It just computes for you this series expansion. So so once again, you can just write down so in the first similar you can write down Gn, which is just essentially related to Cn minus things you can just like flat space. There's just Cn minus things you can complete in EFT. However, you also have to subtract contributions from this particle reduction piece here. But once you do that, you can essentially repeat the same argument that's in flat space, right? You can argue, okay, positive things are positive, it obeys Cauchy-Schwarz equation, and it will essentially carve out some region, which is and it has carved out some region allowed by positivity. Now here in this plot, we have done something more, right? What we have done is the following. So here, chi is some heavy field, and so what we do is we compute the spectral density, and then numerically compute Gn for different values of the cutoff lambda squared, as well as the mass of this change the mass of this particle chi. And in general, as you vary them, it will carve out some region. And you see that for these simple polynomial interaction models, they always lie within the bound of positivity. So that's a good thing. Now let me say a bit more about one of the examples, which is the one loop bubble, right? So this is the region that's carved as this is the region that appears as you change the value of the cutoff and the mass. Now this bound here, this two part of the curve here, BC, they actually correspond to a value of Gn in flat space. So it turns out that this part corresponds to taking the cutoff to infinity while fixing mu. Now you also have this A here, which corresponds to taking the cutoff to zero, and this actually corresponds now in this part of the expression is actually dominated by the contribution from the subtraction of this imaginary guys here. So before I conclude, let me mention one more interesting feature about this series expansion here. So usually you would expect this term to decrease in size as we increase n, right? Now, however, unlike flat space CFT, there are really two energy scales at play here. So first is the cutoff lambda. However, you also have the Hubble scale h here, and we have set this to 1 here. However, if you look at values of nu between the cutoff and h, now something interesting happens here, right? So for example, nu equals 1, so the usual thing happens, right? As you increase n, the size of each term decreases. However, if you take nu to be between the cutoff and h, you find that this term increase and increase in size up to some value n, and then decrease. So what this is telling us is the following, right? So if you truncate the so as you increase n, it actually become between this for these values of nu is actually becoming a so if you truncate n too early, for example, truncate here, is actually a very poor approximation of the sigma EFT here. So there's some optimal value which you should truncate the series at. Anyway, I would like to now I will conclude. Eventually, we'd like to expand. We'd like to apply this kind of technology to realistic inflationary models. So the main challenge we have to face is that generally we might not have a full distance isometry. So we need to figure out how to incorporate, for example, boost breaking interactions. We also like to understand, for example, like how to apply the similar arguments for like more generic diagrams, and And perhaps in the future, we'd like to see whether there's some kind of authenticity statement we can make about the this kind of correlators in the context of the new square plane. So kind of like the similar the usual story in the for complex S plane. And so that's all I have to say. Thank you.